All right, hello. So this lecture is going to be the first lecture on a few on logical equivalence, which will definitely be one of the big things of the first third of the course. We're going to define what it is in this video, and then we will go over what I think is the most straightforward, but maybe also the most tedious way of showing that two statements are logically equivalent. And so without further ado, I might share my screen there so you can all see the notes. We say that two statements are logically equivalent. So this is just given any two mathematical or logical statements. We said that those two statements are logically equivalent if they have the same truth values. And that may seem like an ambiguous definition because it kind of is. So a couple of ways of thinking about this. The first kind of more directly with the definition is that they return identical truth values given identical inputs. So what that means, most of the statements we will be studying logical equivalence for are compound statements, which I put on that second bullet point. And so if you imagine we have two compound statements, each dependent on, say, individual statements P, Q, and R, those two larger compound statements would be logically equivalent if no matter what true false values I chose for P, Q, and R, the two compound statements would always return the same true false value. Maybe another way of thinking about this, and this is kind of the first way we'll use to actually determine whether or not two statements are logically equivalent, is that they have the same truth table. And I'm going to put the same in quotes because really what this means is the same final column of their truth table. That is, if I were to make a truth table for two statements and the columns actually corresponding to those statements, right? When we make a truth table, ultimately we're doing it so we can figure out true false values for larger compound statements. If I make two truth tables and the final columns of those truth tables are the same, those two statements are logically equivalent. And like I'd mentioned, this sort of second way of thinking about this is actually how we'll go about initially showing two statements are logically equivalent. So we've actually already seen an example of two statements that are logically equivalent. So if you'll recall, a statement P implies Q and it's contrapositive, not Q implies not P, are two logically equivalent statements. To write this out, what we often use is a three-lined equals sign. So that three-lined equals sign there is often read as logically equivalent, or just sometimes actually in math, maybe not even logically equivalent, just equivalent. And just kind of a few notes, why don't we use like an actual equal sign? You can think of equivalent as sort of saying that these two things are the same, but not exactly the same. Right? In math, maybe we want the equal sign to be reserved for two things that are literally exactly the same, right? 2 is equal to 2. Both sides of those equal sign are the exact same thing. The statements P implies Q and not Q implies not P, those are two different statements, right? If you remember saying them in words, those are two different statements. And so we don't say they're equal because they're not the same, but they're saying the same thing when we look at them from a sort of pure logic perspective. And so that's why we would say they're logically equivalent, is that they're not the same statement, they're not equal by any means, but logically they're giving us the same amount of, or the same information. So a lot of what we will be doing now for a short period of time is investigating how we can determine if two statements are logically equivalent, and then how we can show that. And like I'd mentioned, the most straightforward way to do this is with a truth table. So I've got two truth tables down here. We're just going to actually go through this for P implies Q and not P, Q implies not P one more time, so I can say what, or show you what I mean again by have these same truth values. So this is a truth table on the left here that I have filled out many times thus far, but I'll fill it out again because it's so important. Remember, the truth table for P implies Q is true, false, true, true. And for not Q implies not P, a false implying a false is always true. A true implying a false is always false. False implying a true is always true, and true implying true is true. And so again, as you can see here, these last two columns of the truth tables, again, the columns corresponding to the actual statements themselves that we're evaluating are the exact same. That means those two statements are logically equivalent. And so here's the thing. When we are looking at truth tables, or when we're studying statements, usually we're not studying statements that are quite as small as just a P implies Q. We might want to, for example, study statements that look like this. P and Q implies R. And I think we've actually seen a statement that looks like that and seen kind of in words how like a statement like that might actually pop up in an argument. And because of that, we might care about maybe showing that, for example, P and Q implies R is actually logically equivalent to not P or not Q or R. That's a logical equivalence that is valid that we will actually prove here in a second. And one that we might occasionally in doing proofs and in logic need to verify. And well, the tool that I've introduced in this video for doing so is using truth tables. And so I actually want to end this short video doing a truth table proof of the fact that these two statements that I've highlighted there are logically equivalent. So question 1 asks us to use truth tables to demonstrate the following logical equivalence: that the statement P and Q implies R is logically equivalent to the statement not P or not Q or R. Just jump right into it. So the truth table for P and Q, this column here, the P and Q column, will be true whenever both are true, false otherwise. And so I'll kind of rush through this column a bit here just to not take up too much time with this video. And now the statement P and Q implies R. Well, this is just a conditional statement where we evaluate P and Q as the left side and R as the right. So the P and Q column will be our left, the R will be our right. True implies a true is always true. Here we've got a true implies a false. That's false. And notice the P and Q column for all of the remaining entries is false. And that means for all of these remaining entries, this column is true. So our goal now is to show that this last column on the rightmost truth table here actually has the same true false values. And it's not enough to just say, well, write them in and say, hey, I'm done, same true false values. We should fill it out and justify why it has the same truth values by evaluating each statement individually. So again, these first two columns I'll probably just go through relatively quickly. Remember, not P is just always going to be the opposite of P. Not Q is just always going to be the opposite of Q. And not P or not Q, that statement will be true whenever at least one of not P or not Q is true. And I have accidentally mistaken. There we go. That would be false. True, 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 true. All right, so now we are on to not P or not Q or R. And this statement, if not P or not Q is true, this statement will be true. Or if R is true, the statement will be true. And so first things first, we can see that here, not P or not Q is false, but R is true. And so this column is true. The second row, not P, not Q is false, R is false, so we get a false. The third row, not P, not Q is true. And if actually you look down here, all of the rest of the entries, I wrote an F where there should be a T. Give me 1 second. There we go. Making some corrections. That should be true. And actually then, if you notice, we get trues all the way down. And sure enough, this column here is the same as this column here. And therefore, those two statements are logically equivalent. All right, so sort of summarizing this video, two statements are logically equivalent if they always return the same truth values. How can you show in a relatively straightforward, but maybe as I've demonstrated with this example, sometimes tedious way that two statements are logically equivalent? Just make two truth tables for both of them and show that you always get the same values.